Artificial intelligence is expanding at a speed the world has never seen before. Governments are investing heavily in semiconductor manufacturing, tech giants are scaling hyperscale data centers, and global investors are pouring capital into AI infrastructure. From cloud computing to advanced machine learning systems, everything is being built for one goal: more intelligence, faster computation, and global digital dominance. But behind this rapid transformation lies a physical dependency that almost nobody is talking about. That dependency is helium. Helium is usually associated with balloons and party decorations, but in reality, it is one of the most strategically important industrial gases in the modern world. It plays a critical role in medical systems like MRI machines, semiconductor manufacturing processes, aerospace technologies, high-performance storage systems, and even AI data center infrastructure indirectly. Without helium, large parts of the modern technological ecosystem would begin to slow down or fail. And right now, helium is entering a structural supply crisis that could reshape multiple industries at once. Before 2026, the global helium market was already tightening due to rising demand from semiconductors, healthcare, and industrial applications. In early 2025, helium prices in the United States reportedly reached around $97,200 per metric ton, reflecting a sharp increase driven by supply constraints and growing industrial consumption. However, the real shock came in March 2026. A major disruption at Qatar's Ras Laffan helium facility changed the entire global supply structure. This site was responsible for producing approximately 5.2 million cubic meters of helium per month, nearly one-third of global supply. Following the disruption, Qatar Energy declared force majeure, instantly removing a massive portion of global helium availability from the market. The impact was immediate and severe. Prices surged across global markets, and supply chains across multiple industries began tightening simultaneously. But helium's vulnerability is not only geopolitical, it is also physical. Helium is stored at extremely low temperatures, around -268.9 degrees Celsius, making it the coldest substance used in large-scale industrial systems. Even under advanced cryogenic storage conditions, helium slowly evaporates over time. Unlike oil, natural gas, or metals, helium cannot simply be stored indefinitely without loss. This creates a unique problem in global logistics. More than 200 cryogenic ISO containers carrying helium became stranded due to shipping disruptions near the Strait of Hormuz. Each container holds high-value material worth millions of dollars, but unlike other commodities, helium continuously leaks through pressure systems. This means that delays do not just pause supply, they permanently destroy it. Once helium escapes into the atmosphere, it cannot be recovered at industrial scale and eventually leaves Earth's atmosphere entirely. This makes it one of the most irreplaceable resources in the global supply chain. The consequences of this shortage extend far beyond industrial gas markets. In healthcare, helium is essential for MRI machines. These machines rely on superconducting magnets that must be cooled using liquid helium. If helium levels drop too low, a failure known as a quench can occur. During a quench, the magnet rapidly loses superconductivity, causing a sudden release of helium gas and rendering the machine unusable. Each failure can destroy equipment worth millions of dollars and disrupt critical medical diagnostics. Hospitals in several regions are already operating with dangerously low helium reserves, in some cases with only a few weeks of supply buffer remaining. This creates serious risks for healthcare systems if shortages persist. The semiconductor industry is also deeply exposed to helium supply shocks. Companies like Samsung Electronics and SK Hynix rely heavily on helium during advanced chip manufacturing processes such as lithography, etching, and cooling. Over the past decade, helium consumption in semiconductor manufacturing has increased significantly due to the growth of AI computing demand. In 2015, semiconductors represented only a small portion of global helium demand. By 2025, this share had increased to more than 20%, largely driven by EUV lithography and advanced AI chip production. At the same time, global governments are aggressively expanding semiconductor production capacity through initiatives such as the CHIPS Act and similar programs in Asia and Europe. Dozens of new fabrication plants are expected to come online in the coming years. However, helium supply growth is not keeping pace. Most semiconductor fabrication plants cannot store large helium reserves on-site due to cryogenic limitations. Instead, they typically operate with only about 1 week of direct working supply. This creates a fragile system where even short disruptions can quickly escalate into production bottlenecks. A single disruption in a high-volume fabrication plant can result in tens or even hundreds of millions of dollars in lost output within days. The AI ecosystem itself is also indirectly dependent on helium. Modern data centers rely on high-capacity storage systems, many of which use helium-filled hard disk drives. Companies such as Seagate Technology and Western Digital manufacture helium-filled drives because helium is 7 times less dense than air. This lower density reduces internal turbulence, decreases friction, improves cooling efficiency, and allows manufacturers to increase storage density inside each drive. For hyperscale AI data centers, these improvements are essential. AI systems require massive data storage for training models, managing cloud operations, and supporting global infrastructure. If helium shortages force manufacturers to shift back to air-filled designs, data centers may face higher power consumption, increased heat generation, and reduced efficiency. This creates a hidden but important drag on AI scalability. Because of these risks, investors are beginning to reevaluate helium as a strategic resource. Large-scale producers, such as ExxonMobil, play a key role in global helium supply. Its Wyoming-based operations represent one of the largest helium production facilities in the world, contributing a significant portion of global output. Similarly, Linde plc controls major storage and distribution infrastructure, giving it strong pricing power during periods of shortage and supply disruption. At the same time, smaller exploration companies are gaining attention from investors seeking high-risk, high-reward exposure. Companies like Avanti Helium, Pulsar Helium, Desert Mountain Energy, and Helium Evolution are developing new helium sources in North America and attracting speculative capital due to their potential growth upside. Russia is also emerging as a key player in the global helium market through Gazprom and its Amur gas processing plant. Once fully operational, this facility could become one of the largest helium production centers in the world, adding a geopolitical layer of competition to an already strained supply chain. The timeline for this crisis is extremely tight. Within approximately 45 days, stranded helium shipments begin to lose value permanently as gas escapes from storage containers. By around 90 days, industrial users may be forced into long-term contracts with alternative suppliers or begin rationing consumption. The deeper issue is that helium demand was already growing faster than supply before the Qatar disruption occurred. This means the current crisis is not temporary. It is structural. The imbalance between demand and supply is expected to persist for several years, affecting semiconductor production, healthcare systems, aerospace industries, and AI infrastructure development simultaneously. The AI revolution is often described as a digital transformation, but in reality, it is built on physical infrastructure and rare industrial materials. Helium has now become one of the most important hidden choke points in that system, quietly shaping the limits of what the future of technology can actually achieve.